This is the first of our 6 free online math sessions, taught by me, Andrew Kai, that's me, and then Ben Wright, Justin Yu, and Luke Robitaille. We're the members of the 2016 MATHCOUNTS Nationals team, and we've placed first, and we're back 4 years later to help teach all of y'all. Now, we'll be covering 6 topics during these sessions, which will be again at this same time from 5 to 6 Central Time on Monday, Wednesday, and Friday this week and next week. So today's topic will be polynomials. And then the next topics, as you can see over here, will be sequences and series, permutations and combinations, angle chasing, similarity, and the last one is number theory. Without further ado, let's move on to the next slide. First of all, a brief self-introduction. My name is Andrew Kai, and I'm a sophomore at Clemens High School in Sugar Land, Texas. I've been doing competition math for 7 years. I started in 3rd grade, and now I'm in 10th. Actually, that's 8. I started in 4th grade, and then I placed second in MATHCOUNTS Nationals twice, and also attended MOPper. And if you all need any, have any questions, as in if you have any questions about when our meetings are going to be, or any of the material I'm covering today, or just anything like that, then please contact me at andrewkai31@gmail.com. If y'all didn't hear earlier, I'm going to mute everyone. I'm going to mute everyone that joins to prevent any spam. And in addition, I'm going to assume that y'all have a solid understanding of Algebra 1 before I begin. So now a brief agenda. First, we're going to be covering the definition of a polynomial, then what a polynomial is and why it's important. Then we're going to be covering operations with polynomials like addition, subtraction, multiplication, and division. Then we'll be talking about looking at roots, which is basically just roots are some of the most important parts of polynomials and are covered in a lot of problems. So we'll be looking at them. Then Vieta's formulas, which are really common in math competitions. It's really important for y'all to learn them. Then the remainder theorem, which is a really beautiful theorem that also helps in a lot of competitions and just in general, it helps a lot. Then finally, we'll be going over a few examples. If you guys need any more resources after this class, if y'all want to apply any of the things that you've learned or whatnot, check out the intermediate algebra section in Alchemist. By the way, I'm currently recording this meeting and I'll be posting it on YouTube afterwards. So if you have to leave in the middle or if you join late, then don't worry about it because we'll be posting it on YouTube and you can watch it whenever you like. Now, without further ado, let's begin. So first, let's cover the definition of a polynomial. I'll be using annotations here. Definition. Oh, sorry. All right, so definition of a polynomial. What is a polynomial and why is it important? Let's cover, first of all, why is it important? Well, polynomials have been the main part of algebra for hundreds of years. The entire field of algebra was only polynomials up until the 17th or 18th century. So obviously these are really important, not just in math competitions, but also in the real world. In math competitions, however, they're covered a lot as well. One of the most common algebra topics. In AMC 8, I think there are a few problems, not many. In AMC 10, there's a few more. But if you get into higher levels like AME or even USMO, there are going to be a lot of problems involving polynomials. So getting a basic understanding of them will be pretty important to advancing yourself in competition math. In addition, not only are they important in contest math, but they're also pretty important as you move on to higher levels of math. So for example, in school, you might be covering quadratics a little, some in Algebra 1. And as you get into Algebra 2, you'll be covering even more about polynomials if you haven't already taken it. And then after that, if you continue in pre-cal and then all the way to college, polynomials will be one of the main things you study if you choose to continue in math. In general, polynomials are really important. So please pay attention and try to learn as much as you can. Now, what is a polynomial? So let's take a variable x, right? Take a variable x. You can take it to some power. For example, x to the 0th power, x to the 1th power, x to the squared, x cubed, so on and so forth. So we have all of these terms. And in fact, a polynomial is just when you add some combinations of these terms up. For example, 2x plus 5 is a polynomial. 5x plus 7 is a polynomial. 2.5x squared plus 3x minus 4 is a polynomial. But then other things let's say square root of x is not a polynomial because it's not a combination of like these terms. For another example is like 1 over x plus 2 is not a polynomial because again, it's not a combination of these terms. I think y'all get the gist. You can only take these terms and then add on coefficients. Now, let me formally define what a polynomial is. There's a lot of variables here, so you might feel a bit scared, but try to keep listening. Polynomial p of x, this is what we call a polynomial. So in terms of x, which is why there's an x here, and the name of the polynomial is p, and that's just to like easily reference it. So p of x would be equal to oh sorry, there's a technical glitch. Give me a second. Give me a second real quick to fix this. All right, is equal to, all right, I'm back. Yeah, is equal to a of n x to the n plus a of n minus 1 x to the n minus 1 plus dot 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 plus a1x plus a0. So you might be confused, like what are these a's over here? These a's are called coefficients. A's are called coefficients. Constant numbers that just like precede each term of x we have here. So for example, like 2 and 5 here are coefficients, 5 and 7, 2.5, 3, and minus 4 are all coefficients, as you can see. These a of n are just like names to call these because you can like have like any coefficients. Like you can have like, for example, like square root of 5 times x cubed, this is the coefficient, or even like complex numbers. Because if you might know I equals square root of -1, then like you can have 3 plus I times x squared. This is also a coefficient. So all these are just called coefficients. Then next of all, n is known as the degree, So basically, the degree is just the exponent, like the highest exponent in the polynomial. In this case, it's just n over here because it's like the biggest exponent. Like over here, the degree would be 2 because 2 is the biggest exponent since we have x squared, x to the 1, x to the 0. And over here, it would be 3. The degree is 3. So to make this a bit more clear, let me plug in like some n's to show you like what kind of polynomials are what. If you plug in n equals 0, you get a special case of polynomials, constants, because plugging n equals 0 means that over here, x to the n is actually just 1. Just p of x is equal to a0. So these are just constants. Some examples like 2, 5, 7, these are all technically polynomials, even though they might not seem like some. Then if you have like n equals 1, then p of x is equal to a1 plus a0. And remember a1x plus a0, sorry. And remember like these a of I like are just like random numbers, but always constant. So no matter what x you plug in here, these a1 and a0 will stay the same. So for example, 2x plus 5, 3x plus 7, and 5x plus 14 are all polynomials. And if n equals 2, you get p of x is equal to a of 2x squared plus a1x plus a0. And again, you can plug in any like values for a to get a polynomial. So if like 2.5x squared minus square root of 3x plus 1. This is a polynomial. And as you can see, it's degree 2 because n over here is equal to 2. And so on and so forth, as you can see. So in general, even if you're like scared of these variables, these random letters like a of n minus 1, dot dot dot, a1, a0, in reality, they're just like expressions like this, like the sum of like anything times like some powers of x. Now let's take a look at these special cases a bit closer. So n equals 0, these three are all constants. And then n equals 1, these three are all linear equations. And n equals 2, this is just a quadratic. And as you can see, like you have constants, linear equations, quadratics, cubics, so on and so forth, as n gets bigger and bigger. And all of these are just polynomials. Polynomials are like a generalization of all these types of equations. As you can see, as I said earlier, they're just a sum of like any like combination of these variable x's. Now, okay, now let me continue. So I'm just going to clear all the drawings, but don't worry because I will have the recording. So all this again will be recorded and saved, and I will post it if you need to take any more notes. Next of all, we know that polynomials can be graphed. So for example, if you have like a polynomial p of x is equal to oh, sorry for that. That's a technical error. You might see that sometimes, is equal to 2x plus 5. You can just graph it as y equals 2x plus 5 on the coordinate plane. It would look something like this or something like that. And then if you have a quadratic, it would, sorry for that again, technical error, it would be graphed like, maybe like this, right? If you have a cubic, then maybe like this. And these curves are just like helpful ways to like visualize polynomials, just like see, like to just like visualize them and help draw them per se. So as you can see, polynomials are just kind of like curves like this if you graph it on the plane. Now that's just another way to express it. Now past that, let me explain the operation with polynomials, which is our next subtopic of today. Operations with polynomials. So if you have two numbers, there are four basic operations: addition, subtraction, multiplication, and division. The same thing applies to polynomials. Just like you add 2 plus 5 equals 7, you can add two polynomials like 2x squared plus 3x minus 4 plus x minus 5 is equal to 2x squared plus 4x minus 9. And let me make this a bit clearer in case you don't understand. You group each term together, which means that over here, if you see 2x squared, there's no x squared. So this is just x squared over here. And then over here, if you see 3x and x sum up to 4x. And then over here, you see minus 4 and minus 5 sum up to minus 9. And in general, this is how you add polynomials. You take each separate term and then just add them up. Now, now subtraction is kind of the same way. So if you have like 2x squared plus 3x minus 4 minus x minus 5. Then to subtract, you would first take the 2x squared term minus whatever's over here of x squared. But there's no x squared term, so it's just going to be 2x squared. And then over here, you see 3x and then minus x. So that's plus 2x. And then finally, over here, you notice minus 4 minus minus 5. So minus 4 minus minus 5 is just plus 1. So this would just be subtracting two polynomials. In the end, it's just taking each specific term, like look at the specific powers of x, and then just add the coefficients, if y'all see what I mean. Now, before I continue with multiplication division, let me also like explain one thing first. So if we have two polynomials equal to each other, right? So 2x squared plus ax plus 5 is equal to 2x squared minus 7x plus b, where like a and b are some variables, right? Then over here, you're going to notice that these two coefficients have to be the same. Same thing over here. So then a has to be equal to minus 7. And then these two coefficients also have to be the same. So b equals 5. That's just a property for any two equal polynomials. Their corresponding things have to be the same. So this is going to be like a really important facet of polynomials that I think y'all should, like, that's really, really important to remember. That if you have two equal polynomials, then these corresponding things will also be equal. Now, next of all, we've only covered addition and subtraction. So now multiplying polynomials. So how do you multiply polynomials? Let's take two different polynomials, in this case quadratics, 2x squared minus 3x plus 10 times x squared plus 4x minus 5. So if we multiply these two, this would, in fact, you just have to do FOIL. FOIL would just be like multiplying two polynomials of the same, you would just multiply every single, every single term with every single other term. So in reality, you would just multiply, I'm choosing the eraser, that's weird. Yeah, so you would just multiply 2x squared and x squared, and that would just be 2x to the fourth. And that's the only product of two terms that can result in something that's that has a coefficient, that has an exponent of 4. And then, next of all, you would multiply the things that in the end have a total exponent of 3. So this would be plus x cubed times 2 times 4 minus 1 times 3. Then after that, you would multiply these three together. So it'll be like plus x squared times minus 2 times 5. Sorry for the mistake over here. Minus 3 times 4 and then plus 10. And as you can see, like this is just because the product of like each of these, this is just going to be something times x squared. Over here, this is just going to be something times x squared. And then these two, the product is just going to be something times x squared. And then we continue with that. So then it will just be like minus 3x times minus 5 plus 10 times 4x. So plus x times 10 times 4 plus minus 3 times minus 5. And then finally would just be the constant term, which is minus 5 times 10. So that's how to multiply polynomials. Just do FOIL. I think some of y'all should already know this. But in general, it's pretty simple. Like just look at every single, just like combine every single term, multiply them together, and look at the ones with the same exponents. Now finally, this is the most difficult, dividing polynomials. Dividing polynomials. So there's something known as long division, which you can use to divide polynomials. So let's say you have some polynomial 3x squared plus 5x plus 7. And you want to divide it by, let's say, x minus 2. Well, we can use long division like this. So you write the first polynomial like over here, plus 5x plus 7. And the polynomial you want to divide like over here. Just like regular division when you divide two numbers. And then over here, you would just see like what times x minus 2 would match this first term, 3x squared. It would just be 3x times x minus 2, right? So it's just 3x and then 3x squared minus 6x. Then you would subtract these two, just like regular division. So 11x plus 7. And then over here, you would just see how many x minus 2's can go into 11x plus 7. And that's 11 because like you can have, if you multiply by 11, then you get 11x minus 22. And then you see this goes into this because these x's cancel out. And you just subtract, which is 29. However, you cannot put any x minus 2's into 29 because as you notice, there are no x's here. So the remainder would just be 29. And that's basically how to divide polynomials. It might be pretty complicated, but there's a lot of practice problems, a lot of practice worksheets out there. And if you want to practice, then you should definitely do it because it's a pretty important algorithm. Now, either way, let's examine this a bit further. So if you divide a number by another number, let's say like if you divide 15 by 7, you notice that 15 over 7 is 2 with remainder 1. 15 is equal to 2 times 7 plus 1, right? Now, over here is kind of the same thing. You notice that you divide 3x squared plus 5x plus 7 over x minus 2. So then 3x squared plus 5x plus 7 is equal to x minus 2 times, over here is 3x plus 11 plus 29. And this is basically like what you're dividing. This is like the dividend. Let me just like, it's just a review of some basic terms. This is just the dividend. This is the divisor because you're dividing by it. And this is the quotient. And this is the remainder. Now, if you notice, the remainder has a smaller degree than the divisor. And in fact, it always has to have a smaller degree. And by the way, remember that a degree is just like the largest exponent, like the largest power of like a term in a polynomial. So like the degree of 29 is just 0 because the largest power is just x to the 0. The degree of this is just 1 because the largest power is just x to the 1, as you see over here. The degree of the remainder always has to be less than the degree of the divisor. Degree of remainder, let me write this down. So degree of remainder is always less than the degree of the divisor. And sorry for my poor handwriting, like it's kind of difficult to write with like a stylus, or at least I'm just bad at it. But anyways, yeah, let's think about this a little bit. So the degree of the remainder over here is 0, and the degree of the divisor is 1. This basically means that over here, you see that, okay, you can't put any x minus 2's in 29. And this is kind of clear, right? Because there are no x's in 29, so you can't put it. However, if there was an x in 29, like in this remainder, like let's say the remainder is equal to x plus 29, then you could put an x, then you could put another divisor over here. So you can subtract by x minus 2 again, then you get 31. And this would be like a new remainder, if you know what I mean. If the remainder was greater than 7, then you can put another 7 into the thing, like into the remainder, and then take that out. So then if it was like 1 times 7 plus 8, you could just take this out and then get 2 times 7 plus 1. Some of y'all might be confused. Well, don't worry too much about the explanation. Just remember this is true, okay? This is the most important part. As you get more used to polynomials, you might be able to better understand like why this is true. But in general, just remember this fact, that the degree of the remainder is always less than the degree of the divisor. And we'll be using that a bit later as well, by the way. Now, so this is how to divide polynomials. We've gone through all 4 operations, and we want to now let's move on to our next topic, which is roots. Oh, sorry for that. Looking at roots. So let's go back to our graphs from earlier. So like we graphed some polynomials, something like this, right? Like these are just like an example of a graph of a polynomial. Let's actually look at when this hits the x-axis, because this is the x-axis over here. So these 4 points are known as roots. Roots, as you see. They're when the polynomial is equal to 0. When the polynomial is equal to 0. I don't know why it's called roots, honestly. Like, it's not really a plant, but that's beside the point. Now, if we have a polynomial, p of x is equal to 2x minus 4, then you notice that 2 is a root, because plugging 2 in here would make this polynomial equal to 0, right? And similarly, like this holds for all polynomials. Like there will always be roots in polynomials. It will always be equal to 0. However, one caveat. These roots can also be complex numbers. Complex numbers. All right, so that's one other thing. If y'all don't know what complex numbers is, remember that if I is square root of -1, then a complex number will be like ai plus b. This is pretty complicated, so don't worry about this material, I guess. Just focus on what a root is. Over here, again, 2 is a root, and every polynomial will have roots. In fact, there's a theorem that hopefully states this. The fundamental theorem of algebra. Theorem of algebra. As you can tell by its name, it's pretty important, and again, it's about polynomials. So there always has to be at least one root. There always exists at least one root of a polynomial. And then, in addition, counting multiplicity, which I will explain a bit more soon, there are exactly n roots. And remember that n is the degree. So like n is the highest exponent of this polynomial. So n is the degree. And yeah, just remember what the degree is. This is a fundamental theorem of algebra, and it is pretty fundamental, as I could say. And I will explain like why, like how we use it and like what it means. This also, okay, so first of all, this means that again, like there exists at least one root. So at least like one place where the polynomial is equal to 0. It might be a complex root. So like if you plug in a complex number, it's equal to 0, but like it might not be real, like a regular number, like 2 square root of 5, these kinds, but there still exists a root. Now let me explain this. This means that you can express a polynomial in terms of its roots, because let's say you have a polynomial p of x, right? This follows from the fundamental theorem of algebra, by the way. And then you have like a leading coefficient a of n multiplied by x minus r1 times x minus r2 times dot 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 times x minus rn. So you might ask, like, what are these r's? These r's are roots. So these r's are roots. Then over here, you can see there exists n roots. There are n roots. Now, you might wonder, like, why is this true? Like, why is this a valid format of a polynomial? Well, if you notice, these r's are roots because if you plug in any r, like plug in any r1, this is just going to be equal to a of n times r1 minus r1 times r1 minus r2 times dot 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 times r1 minus rn. And because this is equal to 0, all of this will be equal to 0. So then r1 is a root. So if you plug in any r of I, then this entire polynomial will be equal to 0, which means that the r of I again is a root. And by the way, when I say like any ri, that just means like anything like from r1, r2, dot dot dot, r of n. These are all variables. To make this more clear, let me give an example. So let's say if a polynomial p of x is equal to 2x squared minus 10x minus 12. Well, in fact, this can be expressed as 2 times x minus 6 times x plus 1. And then you realize that 6 and minus 1 are the two roots. And this is minus 1 because remember it's minus r of n. So instead of plus. So you have to negate this. So this is just x minus 6, 2 times x minus 6 times x plus 1 is this polynomial, right? Like if you learn how to factor quadratics, then this should be pretty clear. This means that if you plug in 6 and minus 1, p of x will be equal to 0, which means that, again, as I said earlier, these are roots. And there are exactly two roots because the degree of this is 2, as it's a quadratic. Remember, the degree is the power of the highest exponent. Now, let's continue. We know this format, right? Like, we know all of this. Well, let's think about it a bit more. What if we want to find like the sum or product of roots, right? Like of all the places where it's equal to 0. That's a pretty common problem in mathematics. And there's actually a pretty cool formula for that, assuming that you know all the coefficients. Let's say you have a polynomial, right? Let's say like p of x is equal to like 3x squared plus 5x minus 9. So you want to know some stuff about the roots. You want to figure out like the sum and product of the roots, right? Let's say you can't actually solve for like what the roots exactly are. And like, let's assume you don't know the quadratic formula. So then you can express this as this in this format over here. So where a of n is the leading coefficient, which is 3. So it's 3 times x minus r1 times x minus r2, right? Where like r1 and r2 are what the roots are called. So then we want to find r1 plus r2 and r1 times r2. And this is just like a pretty interesting, like this is just like we want to find, like we're curious. We wonder what this is. So to do that, let's expand this thing over here. So this is just going to be equal to 3 times x squared minus x times r1 plus r2 plus r1 r2, which is equal to 3x squared minus 3x times r1 plus r2 plus 3r1 r2. Remember what I said earlier. If two polynomials are equal, then the coefficients of each term are going to be equal. So in this case, this and this are equal. So these coefficients over here are equal. And then similarly, the coefficients of x over here are equal. So then minus 3 times r1 plus r2 is equal to 5. And then this coefficient is equal to this. So then 3 is equal, so when 3r1 r2, and sorry, the coefficient is this entire thing because it's just times x to the 0th power, which is 1, which is equal to minus 9. This means that r1 plus r2 is equal to minus 5 over 3, and r1, r2 is equal to minus 3. If this derivation of like why this is true confuses you, then just remember this. The sum of the roots over here is equal to minus 5 over 3, and the product is equal to this minus 9 over 3. let me generalize this. So if you have something like, let me clear this. If you have something like a polynomial, like a quadratic, right? P of x is equal to ax squared plus bx plus c, or like abc or some like random coefficients. Then the sum of the roots are r1 and r2. Remember like r1 and r2 are roots because plugging them in here makes them equal to 0, but we don't know what exact numbers they are. Then the sum of the roots r1 plus r2 is equal to minus b over a. And the product of the roots r1 times r2 is equal to c over a. This is called Vieta's formulas. Okay, I think this is pretty cool because you can, if you just know the coefficients over here, you can calculate the sum and the product of the roots, which is even if you don't know the actual roots. And this isn't just true for quadratics. If you have a polynomial, right? Let's say in general, p of x is equal to a of n x to the n plus a of n minus 1 x to the n minus 1 plus dot 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 plus a1 x plus a0. And then the sum of the roots, sum of all the roots, counting multiplicity will be equal to minus a of n minus 1 over a of n. Then the sum of all pairs of roots, like as in if you take any two roots, multiply them together, and then add the sum of all of that, the sum of all pairs will be equal to a of n minus 2 over a of n. The sum of all triplets of roots. Also, what I mean by sum of all pairs, a pair is like the product of like two roots, so like r1 times r2, something like that. Sum of all triplets, which is just like something in terms of r1, r2, r3, is equal to minus a of n minus 3 over a of n. And so on and so forth, until you get the sum of all, the product of all roots. Product of all roots is equal to like minus 1 to the n of a of 0 over a of n. And let me give an example for this because it might seem like a bit confusing because there's just so many variables over here. So let me give an example. Let's say you have a cubic, right? Let's say like 6x cubed minus 4x squared plus 7x minus 8. So you have this is equal to p of x. Then you want to find the sum of all roots, which is like r1 plus r2 plus r3, if these three are the roots, which is again when p of r1, p of r2, and p of r3 are all equal to 0. So the sum of all the roots, remember, is equal, sorry for that. Okay, it's equal to minus this term over this term. So minus the second term over the first term. So that's equal to 2/3. And then the sum of all pairs is it's like, which is just like, I'm sorry for that again, r1, r2 plus r1, r3 plus r2, r3 is equal to a of n minus 2 over an. So that's the second one, the third one over the first one. So that's equal to 7 over 6. And then the product, which is r1 times r2 times r3, is equal to minus of the fourth one times divided by this. So it's just 4 over 3. So I hope y'all can see the pattern here. Like, as you increase like the number that you multiply together, then you just increase like each term over here. Like you move on from one term to the next and then to the next as you continue down here. But remember most of all that the sum is going to be equal to minus of the second term over the first term, and the product is going to be equal to this last term divided by the first term times minus 1 to the power of the degree. So just remember that. And like these signs over here are going to be alternating. So like minus and then plus and then minus and then so on. Now, since we have these, this is called Vieta's formulas. Again, it's pretty cool because it allows you to find like the sum, the product, the pairwise sum, like all these properties of the roots without actually finding the roots themselves. Because again, sometimes the roots might be really messy. Like they could be like square root of like 174 plus 2 plus square root of 65. like this could be a root of a polynomial, but obviously it's really hard to find it, which means that, but like the sum could be also really, really nice. Like the sum of the roots, even if this is a root, the sum of the roots could be just equal to 7. And you can just find the roots, you can just find the sum using these coefficients. So why is Vieta's formulas important in competition math? Well, there's a lot of questions asking like, what's the sum of the roots of this quadratic, or like the product of the roots of this quadratic, or so on and so forth. A lot of questions of that style, which means that since we know that it's just minus of the second coefficient divided by the first coefficient, then we can just solve for that super, super easily, instead of spending ages of time calculating the actual roots and then adding them up. Now, next of all, let's cover the remainder theorem. This will be the last topic I'm covering today, and then after that we'll go into some problems. So hopefully these problems can help you understand like the things that I've taught today a little bit better. So the remainder theorem. Remember what I said, like polynomial division. So if you have a polynomial and you divide that by another polynomial, right? So if you have like a polynomial p of x, which you divide by another polynomial, and then you have like this divisor times the quotient plus the remainder. And as this is called the remainder theorem, we want to find what the remainder is. So in this case, in the remainder theorem, we're only looking at divisors who are like linear terms. Linear terms means that the degree is 1. So like, for example, it's like x minus 2, or like x minus 7, x minus 5, things like that. So to find the remainder in these cases, you just have to plug in. Okay, so to find the remainder in these cases, if the divisor is x minus a, the remainder would be p of a. And you might wonder why, because like you have a polynomial p of x divided by x minus a. The remainder is p of a. Let me just make that clear. So you might wonder, why is this true? Well, let me explain. So if you have p of x is equal to x minus a times, this is the quotient times the quotient, right? And then plus the remainder. Then you just plug in a into this equation. So if x is equal to a, then p of a is equal to a minus a times the quotient plus the remainder. And notice that this thing is equal to 0. So you don't have to care what the quotient is. This will always be equal to 0 since these two are multiplied. So the remainder would just be p of a, which is what we wanted to know. Let me show you this theorem in action. So let's say you have a quadratic, 3x squared plus 5x plus 7. And you divide plus 5x, sorry, the x didn't show up. And then you divide by x minus 2. Then what's the remainder? I'll give y'all like a minute to figure this out in the chat. I think y'all can use the chat, right? Wait, can y'all use the chat? Is it working? All right, yeah. So as some of y'all have stated, the answer is 29. So the answer is 29. So remainder equals 29. And let me wait for my thing. This is lagging a little bit since I opened the chat. All right, so the remainder is equal to 29. And you might wonder why. Well, if you just plug in 2 into this polynomial, then it'll be 3 times 2 squared plus 5 times 2 plus 7 is 29. And it's this simple. Like, we just have to plug in 2 to get the remainder, instead of always like dividing it out and then figuring out the quotient, and then from there figuring out the remainder using log division. Another example, let's say we want to divide that same polynomial plus 5x plus 7. We want to divide that by x plus 1. Then what's the remainder? And okay, someone asked, why do you plug in 2? Well, as I said earlier, the remainder theorem just states that if you divide some polynomial p of x by x minus a, then the remainder is just going to be p of a. So plugging in a into the polynomial. So yes, as people are saying, the remainder is 5, if just 5. And that's because, let me get my marker here. Okay, yeah, the remainder is just equal to 5. And that's just, okay, this marker is not working well because the chat is lagging it a lot. Give me a second to get this to work better. Sorry for that, everyone. Right, so the remainder over here, as you can see, is just equal to what's happening. Sorry. Everyone, there are a few technical difficulties, but it is going to be okay. Just give me a minute to get back to here. Right, so the remainder over here is just going to be equal to 5. Yeah. Oh, look, it finally works. All right, and that's just because if you plug in -1 into this, then you get 3 times -1 squared plus 5 times -1 plus 7. That's equal to 5. And let me show you why the remainder theorem is actually like so important instead of just dividing and finding the remainder. Let's say you have a polynomial like 100x to the 100 plus 84 times x to the 99 plus 2x plus 1. And you want to find the remainder when this is divided by x minus 1. So what's the remainder? It's going to be pretty hard to divide out, so don't do that. Let me check the chat. There are a lot of notifications. But I'll give y'all like a minute or two to do this. All right, wait, can y'all hear me? Just real quick. Can y'all hear me? Okay, good. My Zoom kind of crashed a little bit because the chat had too many people in it, and too many messages. So I'm not gonna really rely on that from now on. Sorry for the technical difficulties. But anyways, the remainders would just be plugging 1 into this, because as you remember, the remainder theorem is just when you divide by a linear term, like x minus a, and the remainder would just be p of a, so plugging 1 into this. So it would be 100 times 1 to the 100 plus 84 times 1 to the 99 plus 2 times 1 plus 1. And as you can see, this would just be equal to 187. And remember that you plug in 1, not -1, because over here it's x minus a, so then a would just be equal to 1. I hope you all understand this example. Now let's move on to a few problems now, because we've covered the remainder theorem. First of all, this first example I have over here is find the positive real number x that satisfies the equation x squared minus 1 squared minus 1 is equal to 9800. To solve this, we can first take the -1 to the other side, right? Actually, I'll give y'all a minute to read this while I try fixing these technical issues again. This should be like pretty simple, more of a warm-up problem. All right, since we're running a bit low on time, I'm going to start explaining it. So you have over here x squared minus 1 squared is equal to 9801. And this is just because we can move the -1 to the other side. Well, now because of that, we know that x squared minus 1 is equal to 99 or minus 99, just by taking the square root of that. So now we can take this 1 to the other side. So x squared is either equal to 100 or minus 98. And just like me writing these two here is just kind of like an or over here. You might wonder, like, this is minus 98. Does that mean that x can be a complex number? Well, it cannot. Let me explain why. Let's read the problem over here. It says positive real number. That means that x squared can't be a negative number. So the only case is x squared equals 100. Now this case means that either x is equal to, and please stop requesting remote control of my shared content. X is equal to 10 or x equals minus 10. The x equals 10 case satisfies because please stop requesting control of my shared content. I need to teach right now. Either x equals 10 or x equals minus 10, right? Well, that means that we have these two cases. However, x equals minus 10 is not the right answer to this question because it's not a positive real number. Remember that this question is asking for a positive real number. So this can't be x equals minus 10. So the only positive real number x is x equals 10. And as you can see, plugging x equals 10 in here does result in this thing being equal to 9,800. I hope y'all understand the solution to this question, and the answer would just be x equals 10. Now, example number 2. Let me clear this real quick. Sorry, again, a bit of technical issues. This will not happen next time. It's just the screen, I can't clear this for some reason. If we have the polynomial 2x to the 4th plus 5x cubed minus 8x squared minus 17x minus 6, and the fact that p of minus 1 equals 0, determine the sum of the roots of this polynomial. Well, if you think about it, we don't even need the second fact that p of minus 1 equals 0. Sorry, we don't even need this fact over here. We don't need it. Let me just put an x over here. Because remember, the sum of the roots is just minus of the second term over the first term. So it's minus 5 over 2. Remember, it's just minus 5. It's just minus of the second term over the first term by Vieta's formulas. So Vieta's. Okay, sorry, my screen is really broken right now. I'm not sure why, but I think it's something to do with like the load of this meeting, like how many people are in here. So sorry for these technical difficulties. But yeah, so the sum of the roots is going to be c minus 5 over 2. Now, example number 3 states, and this is just using Vieta's formulas again. Now, example number 3 states that the solutions of the equation 2x squared plus 5x minus 12 equals 0 are m and n, and find the value of m minus 1 times n minus 1. To find this value, we can again use Vieta's formula. Let me clear the drawings right now. So using Vieta's formulas, we know that the sum of the roots is equal to minus 5 over 2. And since the roots are m and n, that just means that m plus n equals minus 5 over 2. And this is just because Vieta's formulas states that the sum of the roots is minus of the second term divided by the first term. Now, we also know that by Vieta's formulas, the product of the roots is equal to minus 6, which means that mn is equal to minus 6 again. Now, this is again by Vieta's because the product of the roots is equal to minus 1 to the power of the degree, which is just 2, times the last term divided by the first term. That's minus 12 over 2 is minus 6, which means that this expression over here, m minus 1 times n minus 1, is equal to mn minus m plus n plus 1, which is equal to minus 5 over 2 minus 6, sorry, minus 5 over 2 plus 1, which is equal to, this is just equal to minus 2.5. So the answer to this question is just going to be equal to minus 2.5. And as you can see, this is why Vieta's formulas are so helpful, because you might think like, oh shoot, I have to use quadratic formula to calculate m and n, But no, that's not true. You can just use Vieta formulas to simply calculate m plus n and mn. So you can find m minus 1 times n minus 1. Now, the last example. Let's move on. Example 4. Let me clear this real quick, clear all drawings. So let alpha and beta be two solutions of x plus 2020 squared minus x plus 2020 plus 2019 equals 0. Find alpha plus 2019 times beta plus 2019. Well, okay, because I'm typing using a keyboard right now, since my screen is kind of broken, I'm just going to call alpha and beta A and B to make it a bit simpler. For this question, you might be like pretty scared, right? Because you will have to, then you're gonna have to plug, like you're gonna have to expand all this out, like x plus 2020 squared, like that's a really, really big number. And you might not want to do that, right? So in fact, there's a trick for this called substitution. So if you substitute, let's substitute a let's define a variable y. So y is equal to x plus 2020. Then the equation would just be, the quadratic would just be y squared minus y plus 2019 equals 0. Right? Now, if A and B are two solutions of this, there aren't necessarily solutions of this though, because plugging in, because if x equals A, then y is equal to A plus 2020, which means that this is not really a solution, because if x is a solution, if A is a solution, then A plus 2020 is probably not a solution. Let's think about this a bit more clearly. So we want y equals A, we want x equals A to be a solution. Then y equals A plus 20. Wait, okay, sorry. Let me repeat myself. Okay, I think I've said something wrong on accident. So define. Okay, let's say x is equal to A, right? Then y is equal to A plus 2020. So this A plus 2020 is a solution of y squared minus y plus 2019 equals 0. Because again, y is equal to A plus 2020. However, it's not a solution of this because x is not equal to A plus 2020. X is equal to A, which means that in this equation, the solutions are just A plus 2020 and B plus 2020. If you see what I mean, because the solutions of the initial equation are A and B. And now, because y equals x plus 2020, the solutions are now A plus 2020 and B plus 2020. So these solutions are A plus 2020 and B plus 2020. Now, we're trying to find A plus 2019 times B plus 2019. So in that case, if you notice, A plus 2019 times B plus 2019 is equal to A. Please don't request remote control my shared content. Now, yeah, if you request remote control my shared content, then what happens right now, what I'm doing right now is like stopped in the middle. So I have to retype everything. Actually, let's define two new variables. So C equals A plus 20 and D equals B plus 2020, right? Plus 2020. And by the way, this problem is like a bit difficult. So if you don't understand, don't worry, because like this is more like AMC 10 level rather than just like AMC 8. Well, for this, okay, now we have these solutions of this quadratic are C and D. So solutions, which means that these are C and D, because the solutions of here are A plus 2020 and B plus 2020. So solution of this quadratic, y squared minus y plus 2019, are C and D, which means that we can find C plus D and C times D. C plus D using Vieta's formulas is equal to 1. It's just minus 1 over 1. And then C times D is equal to 2019, because it's just, again, 2019 over 1. The last coefficient over the first coefficient. So now we know C plus D and CD. And we can finally solve this by finding A plus 2019 times B plus 2019. Because we know that A plus 2019 times B plus 2019 is equal to A plus 2020 minus 1. Let me extend this a little bit. A plus 2020 minus 1 times B plus 2020 minus 1, which is equal to C minus 1 times D minus 1. C minus 1 times D minus 1. And this is just because C is defined as A plus 2020 and D is defined as B plus 2020. So in reality, we're just trying to find C minus 1 times D minus 1. However, we know that C minus 1 times D minus 1 is equal to CD minus C plus D plus 1. And guess what? Because of Vieta's formulas, we already know what C plus D and CD are. So this is just 2019 minus 1 plus 1. So the answer is just 2019. And again, this might seem a bit complicated, but here's like the main concepts of the problem. First of all, if you have an equation like something like x plus 2020 squared, where this isn't just a single variable, then you should substitute like y equals x plus 2020. Then next of all, if you have a new quadratic, you can work with solutions of that to make it a little bit easier. And just remember the main things of polynomials, like the most important part of polynomials is remembering Vieta's formulas, because those are used a ton. And when I say a ton, I mean like most polynomial questions in like AMC 8, AMC 10, or like further involve Vieta's formulas. Just remember, so if I want you to take one thing out of this meeting, I just want you to remember Vieta's formulas. And this is the last example for today. I guess our meeting is basically over, and it's like pretty good timing since it's 6 o'clock. So as a final thing, I'll just say a few more words. This is the first meeting out of our 6 sessions. However, I think this is also like the hardest topic out of our 6 sessions. So if it felt a bit confusing, then don't worry, because the others will be a lot easier and like a lot less reliant on like a bunch of random variables like this. Second of all, today there are a ton of technical difficulties for me, as in like my screen stopped working, my stylus stopped working. I think Zoom stopped working like once or twice because of what's it called, the chat lagging, and then people just requesting remote control. Next meeting, we'll fix these issues. I think it'll run like a lot more smoothly and with like a lot less disruptions. So I'm sorry for all the technical difficulties, and we'll try fixing those. But in general, I think this meeting went well, and I'm glad I could teach y'all today. Thank you for attending, and I will be posting this on YouTube soon. I will be emailing that out to everyone who signed up using like the same registration email. So don't worry about that, because I got it under control. Thanks for attending, and please come on Wednesdays at the same time from 5 to 6 Central.